Hi, in this video, I'm going to go through the AQA AS-level Chemistry paper. This is paper 1, and it's the 2019 paper. And I'll just do the first half of the paper in this video and the second half in a later one. Okay, so the first question about compounds that contain fluorine. Sodium fluoride contains sodium ions and fluoride ions. They both have the same electron configuration. Explain why a fluoride ion is larger than a sodium ion. Okay, so we just have a look here. We can see that the fluoride ion, right, let's have a look at fluorine. You're going to have 1s2, 2s2. The fluorine atom has got 1, 2, 3, 4, 5 electrons in 2p. Of course, you gain an extra electron to form the F- ion, so it's 2p6. Now let's see what happens with sodium. With sodium, the sodium ion, you have got there, you've got 1s2 again, 2s2, 2p6, it's full up, and then you've got one electron in 3s here, and of course that is lost to form the sodium ion. So they've both got this same electronic structure. Right, now why is the fluoride ion larger? Well, if you look at the number of so they've got the same number of electrons filling the same quantum shells, but if you look at the so we give you 1 mark for that, but if you look at the atomic number of sodium, well, sodium is 11, whereas fluorine is only 9. Okay, so fluorine has only got 9 positive protons holding in those electrons. Sodium's got 11. It's got a greater positive charge, so the electrons are held closer, and the ion smaller. Next question. Explain in terms of structure and bonding, so 2 marks, why the melting point of sodium fluoride is high. Well, you obviously need to say that it is an ionic compound, and there's strong electrostatic attractions. Between the negative fluoride ion and the positive sodium ion. I think that will give you the 2 marks there. Ionic compound. All ionic solids have high melting points. Right, this is okay, so the next question. The H2F is formed, F plus ion is formed with hydrogen fluoride gains a proton as shown. Name the type of bond. Okay, so just to, it's a dated bond, but let's just have a look. So we've got the dot cross diagram. There's fluorine, there's hydrogen. In the overlap, we have a shared pair of electrons. Fluorine has got 7 electrons in its outer shell. So it's got 3 lone pairs as well as that bonding pair. And it can form a dated bond there to an H plus ion. So this hydrogen, the red one, has come without any electrons. Both of the electrons in the covalent bond are provided by the fluorine. It's a dated bond. Okay, to a dated bond, I think all you need to say for that are both shared electrons come from the fluorine atom. Whereas usually in a covalent bond, the normal covalent bond, 1 electron comes from one atom, 1 from the other. Right, fluoroantimonic acid, not something that anyone will be familiar with, contains 2 ions. Draw the shape of the SbF6 ion and the shape of the other ion, okay? Okay, so first of all, you probably need to look at where antimony is in your periodic table, and antimony, Sb, it's in group 5, like nitrogen and phosphorus. So it's going to have 5 electrons in its outer shell. So let's just draw a quick dot cross diagram there. Then, so we're going to have antimony, and it's got 6 fluorines. Okay. You wouldn't draw this as part of your answer. This is not required. This is just to explain. Right. So there's your antimony, and you've got 4 normal covalent bonds there. So you've got, and that is all 5 antimony electrons accounted for, say they're the dots. Of course, each fluorine has also got 3 lone pairs. We won't draw them on everything. This has got a negative charge. So this last one, right, this fluoride, this has been a fluoride ion, which has come with its own electron, own extra electron, an F minus. So this is essentially a dative bond, this one here. Both of the electrons come from the fluorine, not from the antimony. But the important thing is we've got 6 bond pairs, and we've got no lone pairs. 6 bond pairs, what shape do we get? You will get an octahedral shape, so that's the name of that ion. And we have to show a diagram for it. Now, I'll draw it properly, but you don't actually need. So we've got SB. Now we've got 4 in the same plane, 2 going backwards and 2 coming out of the paper towards you. They're in the sort of square plane a bit. And then you have one fluoride going down and 1 going up. Okay, so it's going to be octahedral. You don't have to draw the wedges and the dotted lines. As long as you draw 6 bonds and no lone pairs, you'll get the mark for that. Right, now let's do the shape of the H2F plus ion. Well, I've already drawn a dot cross diagram for that up here. So let's just let's have a look at that. Right, there's the H2F plus ion. The whole thing has got a positive charge, of course, because the red hydrogen came without any electrons. Right, what have we got there? We have got 2 bond pairs and we have got 2 lone pairs. So that's like 4 pairs altogether. So the arrangement of the orbitals is going to be tetrahedral. So if we draw that, we've got fluorine. We're going to have 1 lone pair there. Let's say we've got another lone pair there in the plane of the paper. And you've got this bond coming out towards you, the hydrogen. This bond going back into the paper. That hydrogen, there's it's tetrahedral. Normally the tetrahedral bond angle is 109.5, but of course, because you've got 2 lone pairs and they cause greater repulsion, this angle is down to about 105.4.5. Just like the bond angle in water, it's essentially like H2O. And the shape of that molecule, you would probably call it, well, you can call it bent or V-shaped. Okay, so there's your 4 marks there. Okay, and then the shape of each ion. V-shaped is this one here. Yeah. It doesn't actually ask you for the bond angles, but we've given them anyway. Okay, and it's important to show those 2 lone pairs on the on this one, on the H2F. All right. Right, this is a bond energy calculation question then. So hydrogen fluoride reacts with ethyne there, as shown in the equation. All compounds in the gaseous states, and we've got the mean bond enthalpy data. They give us the enthalpy change for this reaction. It's minus 179 kilojoules per mole. They give us all the bond angles except for these 2 CF bonds here, and we've got to calculate the bond enthalpy of the CF bond. Okay, so the way I like to do these is I've written the equation down there. First of all, we're going to break every bond here to form the gaseous atoms. So we're going to have 2 carbon gaseous atoms. We're going to have 2 hydrogen gaseous atoms. That's not H2 molecules, obviously, it's separate atoms. And sorry, we're going to have 4 hydrogens there, aren't we? Not 2. And we're going to have 2 fluorine gaseous atoms, again, not F2. All right. And then we're going to build them all back up together again in that direction. That's making bonds. Right, so which bonds are we breaking here? We're breaking, okay, we're breaking the carbon-carbon triple bond. So that's a positive value because it's endothermic, so it's plus 837. We're breaking 2 carbon-hydrogen bonds, so that's 2 times 412. And we're breaking 2 hydrogen fluoride bonds, which are 562. Right, let's add that lot up together, and we get 2,785 plus 2,785. Right, making bonds now. Well, we're going to make one carbon-carbon single bond, so that's 348. That's going to be minus because it's exothermic, making bonds, energy released. We've got 4 times the carbon-hydrogen bonds, 4112. That's going to be minus as well. And we're making 2 of these carbon-fluorine bonds. We don't know what they are, so let's call them X, so it's minus 2X. So let's add that lot up together, and we get minus 1,996 minus 2X. Okay, now we know that this change here, they tell us in the question, delta H there for the reaction is minus 179 kilojoules per mole. So I am going to write down there the, well, let's do it over here. So we know that the yellow arrow, that's minus 179, is the same as doing the green arrow. So that is going to be minus 2,785. And we are making bonds here. Sorry, that's going to be plus, sorry. So that's going to be plus, sorry, minus 1996 minus 2x. Okay, so let's just group all those terms together, and we get 968 is equal to 2x. So that means x is equal to 968 over 2, which is equal to 484. So the bond energy of the CF bond is 484 kilojoules per mole. I'd always use that energy cycle when you are doing bond energy calculations. Right, time of flight mass spectrometry. Right, we've got a mixture of 3 compounds analyzed in the mass spectrometer, and it's ionized using electrospray ionization, not by electron bombardment. Okay, and there are 3 compounds they've given in there. Describe how the molecules are ionized using electrospray ionization. Well, first of all, the what you need to say is right, you dissolve this stuff in a volatile solvent, low melting point solvent. Okay, so the sample dissolved in a volatile solvent, and it's passed through a needle at a high, in other words, a positive voltage. Okay, and what that tends to do is it makes a proton. A proton is transferred from the solvent to the sample molecule. So that's what you need to write for your 3 marks, and the proton will form a dated bond to a lone pair somewhere in the molecule. You don't need to say that though, and so it will gain a positive charge, and it will also gain an extra 1 mass unit as well. But you don't need to say that. Okay, give you the formula of the ion that reaches the detector first in the mass spectrometer. Okay, right. Well, we need to work out the MR of those things first. Okay, so the MR of, we need to find out which one reaches the detector first. Which one's going to get there first? Well, it's going to be the lightest one. So we need to work out the MR of those things. So the MR of that one works out to be 87, and that one is the lightest. This one is 105, and this one is even heavier still, 121. Right, so this is going to be, this molecule here is going to be the one that reaches the detector first, but of course it's going to gain an extra proton, so it's going to be C3H6, not H5, O2N, and it's gained a proton, so it's got a positive charge. Okay. 2.3, a sample of germanium, so this is an element now, is analyzed using electron impact ionization, which is different. Okay, so what happens then is well, it's asking for the equation there. So we've got germanium atom, and it's going to be in the gaseous state. An electron is going to impact with it, and it's going to knock an electron out, forming a 1+ ion, and we'll have an electron there. Okay, and everything's got to be in the gaseous state, so that's why it's talking about the state symbols there. Right, and here's a time of flight calculation now. Right, okay. Right. Okay, so it gives us the time, t, the time for the time of flight. It gives us the kinetic energy, we know that. We know the length of the flight tube, let's call that d for distance, we know that. It gives us the Avogadro constant, L. Use this information to calculate the mass in grams of one of those germanium ions, okay, and use your answer to state the mass number of the germanium ion. So, well, we've got to find out the mass of the ion. So here's our equation. We know that kinetic energy I'll write it down at the bottom here. Okay, we know that kinetic energy is equal to half mv squared. Right, we also know that velocity is equal to the distance over the time. So in other words, v squared is equal to d squared over t squared. So I'm going to substitute that in. So we're going to get kinetic energy is equal to a half mass of the ion, d squared over t squared. Right, now that will give us the mass of the ion in kilograms. Okay, so let's rearrange that to get m. So we rearrange that, we get m is equal to the kinetic energy multiplied by t squared over a half d squared. Right, let's put the numbers in there then. So kinetic energy, they tell us is, let's have a look, what number is it? 2.438 times 10 to the minus 8 joules times 10 to the minus, not 8 was it, 10 to the minus 15 joules. 15 joules multiplied by the time squared. The time is 4.654 times 10 to the minus 6 seconds. We need to square that, divided by a half, multiplied by the distance, the length. Now the length is 96 centimeters. 96 centimeters, we've got to put that into meters. Obviously that's 0.96 meters times 0.96 squared. So the units are really important there. Put all the numbers in there and you get m is equal to 1.14597. I've given too many figures there. We'll worry about them in a minute. Times 10 to the minus 25 kilograms. We need to convert that into grams. So multiply it by 1,000. So that's 1.14597 times 10 to the minus 22 grams. Okay, now we're in a position to try and so we know the mass. We've done that first bit. We've calculated its mass in gram of one ion, but we need to find out for the mass of 1 mole. Now, if one ion weighs that much, how much does 1 mole weigh? Well, we need to multiply that by the Avogadro constant. So 1 ion has a mass there. So 1 mole of ions, in other words, 6 times 10 to the 23 ions, is equal to 1.14, I'll just call that 146, times 10 to the minus 22, multiplied by the Avogadro constant, 6.22 times 10 to the 23. that gives us in grams 69.01 grams. Right, now we've got to state the mass number of this germanium ion. Well, mass number is going to be whole numbers, number of protons plus neutrons. So the mass number must be 69. That is our answer. Okay, slightly different take on the time of flight calculation than they usually ask, where quite often they ask you to work out the time of flight. They're giving you the time of flight there and you have to work things out backwards. But it's all about having your two equations there. You need to know that equation, and you need to know this equation, and you need to be really careful about your units, masses in kilograms, distance in meters, time in seconds, energy in joules, SI units. We don't usually use kilograms in chemistry, but we do in this particular place, in this particular topic. Okay. Right, on to the next question about chromium and its compounds. Complete the full electronic configuration of a chromium atom. Okay, right. So we have got 1s2 is filled up. 2s2 is filled up, 2 electrons in there. 2p is going to be filled up with 6 electrons there. 2p6. Move on to 3s. That's filled up. 3s2. 3p is filled up, 6 electrons. Then we have to be a bit careful now. We're going to fill up 4s, okay? So 4s, so I'm going to put 4s2 there. And then the d electrons, we have got 1, 2, 3, 4, 3d4. Now, if you thought that was the right answer, of course, that's a bit of a trick there because that's not the right answer. It's an unusual case with chromium. So that you have a half-filled D shell, one of those electrons from the 4s, and so you have one in the 4s, and that goes in the 3d. So that's 3d5. Okay, similar thing with copper. Do you remember that as well? It's not 3d, it's 3d9, it's 3d10, and it borrows one from the 4s. Okay, right now. Right, an atom has 2 more protons and 3 more neutrons, an atom of chromium 52, 1 mark. This is actually a bit more to this question than you might actually initially think. So let's look at chromium, what we've got there. The chromium, the atomic number for chromium, Z, protons for chromium is equal to, the atomic number is 24. Okay, so this new atom, how many protons has that got? It's got 2 more, so it's going to be 26. Now it's got 3 more neutrons in chromium 52. So neutrons in chromium 52, we have to do that. In 52 chromium, well, that's going to be 52 minus 24, which is equal to 28. And it tells us here we've got 3 more neutrons. So this other atom, the other atom has neutrons. It's got 28 plus 3, so that makes 31. So let's do the mass number of this new atom. So that's going to be 31 neutrons plus 26 protons, which is equal to 57. And we know that the atomic number, what it's got, we know the atomic number, it's got 26. So that means which element has 26 protons? You look here, it's iron. So the answer here is Fe2657. There's quite a few little sums to do in that, more than you think for 1 mark. Okay. Now, relative atomic mass calculation from abundance of elements. Okay. A sample of chromium contains 4 isotopes and it's got a relative atomic mass there. We've got the mass number and the percentage of these in the table, right? So determine the percentage and abundance of the fourth isotope. Well, they've all got to add up to 100, so that's pretty easy. So this fourth one, let's call this X, is going to be 100 minus 82.8 minus 10.9 minus 2.7, and that gives us 3.6%. Okay. Now, how do we work out relative atomic mass? Relative atomic mass, we do, is equal to the sum of the of all the isotopes for the abundance multiplied by the mass number for each one. So let's put the numbers in there. So we know that it's 52.09. Now these abundances, it's much easier to, instead of using percentage, is to turn them into fractions or decimals. So that's 0.828, that's 0.109, that's 0.027, and this is 0.036. Let's put the numbers in. We get so 0.828 multiplied by 52 plus 0.109 multiplied by 53 plus 0.027 multiplied by 54 plus this last one, 0.036x. Let's just do a little bit of calculation there. So we got 52.09. Now you add all that lot up there. I do that on my calculator. It's 50.291 for that, plus 0.027. Sorry, plus 0.036x. So simplify that. We're going to get 1.799 is equal to 0.036x. X is equal to, divide that, 1.799 over 0.036. That gives us 49.972. Right, so the mass number, the closest whole number to that, is obviously got to be 50. There's our answer. Okay, so again, rather than working out the relative atomic mass given the abundance and the mass of the isotopes, you're kind of doing it backwards, which is, they seem to do that more often because it's a bit more difficult. Okay. Right, redox now. Right, deduce the oxidation state of chromium in the dichromate ion, this thing here, which you come across a lot in year 13, but you haven't come across in year 12. Right, so it's, you come across the oxidation of alcohols. Right, so we're going to use the sum of the oxidation numbers is equal to the charge on the species. What's the charge on this species? It's -2. Right, we've got 2 chromium atoms. We don't know what they are, so let's call them 2Cr. That's the oxidation number of chromium. We've got 7 oxygen atoms. Each one of those oxygen is always -2, so that's going to be -14. So 2Cr, add that 14, is equal to +12. Divide by 2. Chromium's oxidation number is +6. Okay. Iodide ions can be oxidized to iodine. Deduce a half equation to show the oxidation of iodide ions to iodine. Okay, let's do that. Right, so we've got iodide ions, I-. I'm going to oxidize, you're going to remove an electron, turn it into I2. I'm going to double that to balance it. Now we need to balance for electrons. We've got 2 minuses on the left and 0 on the right, so we need to put 2 negative electrons on that side. The next thing they're going to ask us a half equation for the conversion in acidic solution of dichromate to chromium 3+. Let's do that. Okay, so we've got dichromate, CrO272-, and that's going to go to chromium 3+. Right, the first thing we need to do is balance it for the number of chromium atoms there, so we need to put a 2 there. Next thing we need to do is we need to balance for the oxygens with water molecules. We've got 7 on the left and none on the right, so I need to put 7H2O on that side. The next thing we do is balance for hydrogens. Well, I've got 14 hydrogens on the left and I haven't got on the right 14 there, and I haven't got any on the left, so that means I need 14H plus. The last thing we need to do is to balance for charges. So let's see what charges we've got on the right, on the left. The left, we've got a 2 minus and a 14 plus, so that means we've got plus 12 on that side. On the right hand side, it's easy to forget this. Look, you haven't just got one Cl3 plus, you've got 2 of them, so that's going to be plus 6 there. So somehow we've got to have the same number of charges on both sides of the equation by adding electrons. Well, we can do that if we add 6 negative electrons there, so 6E minus. That is our half equation. Okay. Right. Now use your answers from here and here to write a fully balanced equation for the oxidation of iodide by dichromate. Right. So we look here, this is a 2-electron process and this is a 6-electron process. So we're going to have to multiply this equation by 3 before we add them together. So if we wrote our final equation, it would be multiplied by 3. We've got 6 iodides. Don't multiply this one by anything, just one dichromate ion. 14 protons. And that's going to give us, 3 times I2, so it's 3I2. And we're going to have 2 chromium 3 plus ions and 7 H2Os, water molecules. Right, that is the final answer there. Okay, now this is a 6-mark question about first ionization energies and how they change across a period. This is unusual to have a 6-mark question. They always ask this, but it's usually broken down into smaller bits. So it says here, explain the pattern in the first ionization energies of the elements from lithium to neon. Right, now you wouldn't draw this graph in your answer, not at all. I've just drawn it. You're probably very familiar with this graph just to explain it. So you can see, right, what we're going to say. We've got lithium, beryllium, boron, carbon are going across period 2 all the way to neon. So let's talk about the electrons. Where have these electrons come from, the first electron? Well, in lithium, the electron's coming from 2s. Beryllium, it's coming from 2s. Boron, it's not coming from 2s, it's coming from 2p. And the rest, these next lot of elements, you've got the electron is always coming from 2p. So we've got to explain the pattern. So for the first thing I would say is, as you go from left to right, the first ionization energy, the general thing is it increases as you go from lithium to neon. Why does it increase? Electrons have been removed from the same quantum shell, i.e. number 2. So that means you've got roughly the same distance from the nucleus. Okay, but why does it increase as you go across? Because the nuclear charge is increasing. Nuclear charge, a positive pull of the nuclear charge, so the positive charge holding onto those negative electrons increases. The nuclear charge increases as you go across. So lithium is it's got 3 protons, neon has got 10. So it gets bigger. Right. So the general thing is for it to increase, but we have got, obviously, we've got 2 differences there, 2 little drops where it doesn't fit that general pattern. And we've got to explain each of those 2 differences. So I think probably 2 marks for this bit. We're going to get 2 marks for these next 2 differences, that one and that one. Let's do the first one between beryllium and boron. Why has boron got a higher first ionization, lower first ionization than beryllium? So let's talk about that. So we're going to say beryllium is going to be lower because the electron removed from 2p, and for beryllium it's from 2s. And I think we need to say that 2p is a bit closer to the nucleus, ever so slightly closer to the nucleus than further away from the nucleus, sorry. 2s ever so slightly, or you could say it's higher in energy. That would be fine to say that. And so that you don't need quite as much energy to remove it. Right, now this second deviation here, what's going on? That's between nitrogen and oxygen. Now we need to explain in nitrogen, all 3 p electrons are unpaired. So if you look at, you've got 3 p, you've got the electrons don't go in the same orbital, they have parallel spins in different orbitals. When you go to oxygen, then you have one of the electrons is paired. So I'd say one electron is paired up, one electron in the p orbital is paired, and you get some repulsion from the paired electron. So as I say, I think you get 2 marks for the bit in black up here about the general trend, and you get 2 marks for each of those, roughly anyway, 2 marks for each of those 2 deviations. With these 6 markers, there's always some kind of element of like how coherent is your answer generally, but that's how it all breaks down. Right, now we have a question on equilibrium here. So nitrogen monoxide reacts with chlorine to form this compound here. Right, and it tells us, right, we've got to calculate equilibrium moles. So what I would always do is you're going to write down the equation, then write down this start moles, used up moles, equilibrium moles, and then we read the question carefully. Very common, these questions, practically one on every paper. So the start moles, let's have a look here. 1.5 moles of NO, so that's going to be 1.5 moles of that, 50 moles of that, are mixed with 1 mole of chlorine, and we haven't got any NOCl, so 0 there. Right, now it tells us that the equilibrium mixture contains 0.35 moles of the product. Okay, so that's 0.35 moles of that. So let's see how much of NO has been used up. Right, 2 moles of NO give 2 moles of that. So we've obviously used up 0.35 of that. So how much of that one have we got left over? Well, we're going to do 1.5 minus 0.35, which gives us 1.15 moles. Now let's look at the chlorine. Well, there's several different ways of doing this, but look, if we've used up 0.35 moles of that, every time we use up 2 moles of that, we only use 1 of chlorine. So the amount of chlorine used up is 0.35 over 2, which is equal to 0.175. So how much chlorine have we got left over at the end? We've got 1 minus 0.175, which gives us 0.87825, moles. So there's our 2 answers there. 1.15 moles of that and 0.825 moles of that one, of the chlorine. Now, they don't ask you to work out Kc from that in case you got those bits wrong and you wouldn't be able to get it. So they always say, right, just give us the expression for Kc now. So let's look at the equation there, just get the equation view. So we can see that Kc products, so it's concentration of NOCl, and we have to square that because we've got 2 there, divided by the concentration of NO, and we square that because we've got a 2 in front of it there, multiplied by the concentration of chlorine. That's our equation there. Okay, 5.3. Now, different mixture. Okay, this is in case you get the other bit wrong. Is prepared in a flask of the volume 800 centimeters cubed, and they give us the number of moles of NO and chlorine, and they give us Kc as well, and we've got to work out the number of moles of NOCl. Now, the main way people, and it's 4 marks this question, the main way people make mistakes here is they forget that these square bracket things mean the concentration. They don't mean the number of moles, and of course concentration is equal to the moles over the volume. The volume they give us is 800 centimeters cubed, so that's going to be moles dm cubed is going to be 0.8, isn't it? Okay, so all we have to do is put in our numbers into this Kc expression, and we should be able to find out the number of moles of NOCl. Okay, right, so let's put the numbers in there. Right, so Now, the moles of NaCl, I'm going to call that X, okay? We've got to find out here. Moles of NaCl, let's call that equal to X. So I'm going to put the numbers in here. We're going to have Kc is equal to, now there's some moles of NaCl, but we want the concentration, so we've got to divide by 0.8. So it's X over 0.8 all squared divided by the moles of NO, 0.85. 0.85 divided by the concentration, by the volume, sorry, 0.8, and that's all squared, multiplied by the chlorine, number of moles of chlorine, we have got 0.458 over 0.8. You don't have to square that or anything. Okay, so I'm going to simplify that. That gives us Kc, sorry. I'm going to multiply these brackets out. Kc gives us X squared over 0.8 squared. And that's 0.85 squared over 0.8 squared, multiplied by 0.458 over 0.8. Now you can save yourself a little bit of plugging numbers into calculators doing it this way, because you can cancel out some stuff here. You can see that that 0.8 squared is going to cancel out with that 0.8 squared. So let's just rearrange that equation then. So we're going to get Kc is equal to X squared over 0.85 squared multiplied by 0.458. Now that is going to go up to the top line, so that's X squared multiplied by 0.8. Right, all we need to do now is put the number in for Kc and rearrange, so we end up going to get there X squared, put all our numbers in, is equal to 0.85 squared multiplied by 0.458. Let's go to the top line, multiplied by the Kc, which is 1.32 times 10 to the minus 2, they tell us, divided by that 0.8 comes down to the bottom. So I get X squared there is equal to, put all those numbers into the calculator. X squared is 5.45 times 10 to the minus 3. Take a square root of that. X is equal to 0.07389 moles. Okay, that's the number of moles of NaCl. Now it's significant figures. Let's give it to 3 significant figures. 0.0739 is our answer. Now that is as far as I'm going to go with that paper, because the next question I am going to do in the next video. I'll do the next question and the multiple choice in the next video.